What's up, everybody? It's Mr. Prevet. We are here doing another FRQ review. We are on the final question of the 2022 AP test, number 6 of the FRQs. We got a particle motion question to deal with today. So it should be exciting. Looking over this question, it honestly doesn't look too bad. It looks very approachable. So yeah, I'm excited to dive into this together with you guys. I really appreciate y'all's support as always. It means a lot to me. I really hope that these videos are helpful and that you're learning from this because I really want you to succeed on your AP exam and in life in general, right? We'll generalize it to everything. But we can go ahead and dive right in. So let's read it together. It says particle P moves along the x-axis such that for time t is greater than 0, its position is given by xp of t equals 6 minus 4 times e to the negative t. Particle q moves along the y-axis so that for time t is greater than 0, its velocity is given by v of q of t equals 1 over t squared. At time t equals 1, the position of particle q is y of q of 1 equals 2. Okay, so you've got two particles. Particle P, whoopsie. Particle P is moving along the x-axis, and particle Q is moving along the y-axis. Okay. A lot of times when we see particles moving on opposite axes, we know that we're kind of looking to a related rates question later on, where it'll ask, okay, if this particle's moving this fast, this particle's moving this fast, what is the rate of change of our distance between the particles? And I don't think this question actually asks us that, but it's an interesting concept that I think you guys could explore for yourselves. But let's actually dive into what they ask us about, starting with part A. And part A says, find Vp of t, the velocity of particle P at time t. Now this question honestly is not too bad if we know one simple fact, and that is that velocity is equal to the derivative of position. And this is a big thing, right? But if we take a position function and I take the derivative, that will give me the velocity function. And the great thing is they already gave us the position function. It told us x for particle P, our position at time t, is equal to 6 minus 4 times e to the negative t. So when I take the derivative of this function, I just get 6 becomes 0, 4e to the negative t. I know e to any power, its derivative is just e to the negative power, right, times the derivative of the exponent, which is negative 1. So those negative signs will cancel out, and I will get 4e to the negative t power. And that is equal to the derivative of my position, which is the velocity function. So part A, honestly super simple, just taking a derivative of this function, understanding that the derivative of position is velocity. So that's part A. We can move on to part B, bigger and brighter things, right? So let's check it out. Part B, it says find AQ of t, which is our acceleration of particle q at time t. Find all times t for t is greater than 0 when the speed of the particle q is decreasing. So we're looking for where speed is dropping, it's going down, right? But first, let's find our acceleration of the particle. Very similar to the last question where we were asked to find velocity, acceleration, we know, is the derivative of velocity, right? Velocity is the derivative of position. Acceleration is the derivative of velocity. And once again, we have our velocity function. Our velocity of particle q is equal to 1 over t squared. So if I wanted to take the derivative of this function, I would write it as t to the negative second power, and then use power rule to take this derivative. So I would get negative 2 times t to the negative third power. And that equals my acceleration of particle q. So that is the first half of this question. But now we have to look at the second half, which asks, when is the speed decreasing, right? Or when are we slowing down? Okay. Now here's the deal with velocity and acceleration and how we figure out when particles are speeding up versus slowing down, right? A particle speeds up when velocity and acceleration are pointed the same direction. If they are pointed opposite directions, we're going one way, but we're being pulled the other way by acceleration. We're slowing down, kind of being pulled the opposite direction. So we need to figure out, when t is greater than 0, is velocity positive or negative? Is acceleration positive or negative? So let's look at velocity first, right? So velocity over here is 1 over t squared. Our acceleration over here is equal to negative 2 over t cubed. Let's think about it. Our velocity and acceleration would change signs when it is equal to derivative, or when it is equal to 0, or undefined, right? The only place for either of these functions is 0 or undefined is t equals 0. But t equals 0 is outside of our range, right? We're only looking at t is greater than 0. So if I set up my number line, I'm really just starting at 0 and going this direction for both of these. Because their t has to be greater than 0. There's no critical values where it might change signs. So I just need to check. If I plug in like t equals 1, is my velocity positive or negative? It's positive. If I plug in t equals 1 into acceleration, is it positive or negative? Well, it's negative. So my acceleration is negative, right? But my velocity is positive. So therefore, they're in opposite directions. Acceleration is pulling the particle the other direction that it's actually going. So it's slowing down, right? Or speed is decreasing. And this is true over the entire interval. So I would write our speed is decreasing for all t is greater than 0 because velocity is always greater than 0 and acceleration is always less than 0. And that would be my justification to this question, which I think is all that you need. So because they're opposite signs, that's your answer. Okay? So that is the correct answer to part B. So let's move on. Part C. We're asked about position now. I think generally in particle motion, position, displacement, distance questions, those are normally all way more difficult than like velocity and acceleration questions. And I think it's because it involves integrals. Right? So part C, it says, find y of q of t, the position of particle q at time t. Now, what do we know about this particle q? Well, I know that my velocity of q is equal to 1 over t squared, or t to the negative second power. Now, how can I find my position function based on that? Well, I know that the derivative of my position function equals my velocity function, right? So if I take the integral of both sides, right? Well, this left side should give me my position function, and that should equal just the integral of my velocity function, right? But then there's going to be some plus c floating around in there that we have to solve for, right? So let's take the integral of this velocity function, right? Or I'm sorry, this will be just position. The integral of the derivative of position is just position. So let's take the integral of this function. Using power rule, we would get that our position is equal to t to the negative first power, if I raise the exponent by 1, divided by the new exponent, plus some value c. We're not sure what that value c is, right? So this will be like negative 1 over t plus c, and that is yq of t. So now we have this plus c that we need to solve for. How can we do it? Well, they give us an initial condition. They tell us that yq of 1 is equal to 2. So if I plug in 1, that'll equal negative 1 over 1 plus c. That is equal to 2. So negative 1 plus c equals 2. C is equal to 3. So now plugging that back into my equation, I get that my position is negative 1 over t plus 3. And that is my final answer to part C. So if you are ever asked to find the position of a particle based on a velocity function, right? We're going to integrate the velocity function, right? But there's going to be a plus c. There's going to be some constant that we don't know about, right? And that's going to be our position. We're going to integrate it. We're going to solve for c. And then we're going to just have our position function, which is great. It's not too bad. Just do an integral, solve for c, and we're done. Okay. So that's the answer to part C. We'll move on to part D, which I was saying a lot of times is a related rates question when they're on opposite axes. This time it's going to be something a little different, which I appreciate. So part D, it says, as t approaches infinity, which particle will eventually be farther from the origin? It says, give a reason for your answer. Let's think about it. The particle that's farther away will just have the greater position, right? It'll be further away from the origin. So for particle P, its position on the x-axis was equal to 6 minus 4 times e to the negative t. Now our position of particle Q, which we just solved for on the y-axis, was 3 minus 1 over t. I think we got negative 1 over t plus 3. It's the same thing, right? And we want to figure out, as t goes to infinity, which of these is greater, right? Well, what we can do is take two separate limits as t approaches infinity. Take the limit of 6 minus 4 times e to the negative t. And then we'll also take the limit as t approaches infinity of 3 minus 1 over t. We'll figure out which one of these is greater. So let's start out with this first one, the position of particle P. Well, as t approaches infinity, 6 just stays as 6, right? But this 4 and then e to the negative t power, right? We could also write that it's like 6 minus 4 over e to the t power. So as t gets infinitely big, e to the t also gets infinitely big, and 4 over infinity will approach 0. So 6 minus 0 will just equal 6 as t approaches infinity. And a similar process happens for our second one, particle Q. As t approaches infinity, 3 just equals 3, right? But 1 over t, infinity is like, it's infinitely big, right? So 1 over t is going to approach 0. So this limit will just equal 3. So as t approaches infinity, particle P is going to approach x equals 6. Particle Q is going to approach y equals 3. So which one is further from the origin? The answer is particle P. And that is our final answer to part D. Our reasoning would just be that our limit as t approaches infinity, if both of these functions, when we get it, the limit as t approaches infinity of the position of particle P is greater than the limit of particle Q's position. But we have now wrapped up the entirety of the 2022 FRQs, again 1 through 6. It was a joy and a pleasure to go through all of them. And I really hope that it helped you guys, right? That's the goal of all of this. I want you guys to succeed, right? But thank you so much for watching. I really hope to see you guys on another video very soon.